What if we could power entire cities with the same process that fuels our sun, without any long-term radioactive waste? The answer lies in nuclear fusion, and it's closer than you think. Nuclear fusion allows us to produce massive amounts of energy without the devastating side effects of fission, and it holds a promising future for humanity.
To understand the benefits of fusion, we first need to understand nuclear fission. Two common fission reactions used to generate energy are uranium and plutonium reactions. Nuclear fission is a good way to produce energy, but it is too expensive and has a few downsides, such as the creation of radioactive waste and the prohibitive cost of building a nuclear reactor. The difference between fusion and fission is that fission involves splitting nuclei, such as uranium and plutonium, in order to generate energy, while fusion involves the combination of nuclei, such as hydrogen, to generate energy. Nuclear fusion occurs naturally in the core of the sun and in other stars, and in black hole accretion disks.
NIF, or the National Ignition Facility, uses 192 of the world's most powerful lasers to recreate the extreme conditions found in the sun, where nuclear fusion happens naturally due to high concentrations of plasma. With these lasers, Lawrence Livermore Labs and NIF were able to produce 3 times the amount of energy than they put in. This is called ignition, and it was first done by NIF in 2022. Their experiment produced 3.15 megajoules of energy when only 2 megajoules were put into the reaction. The fact that this has been replicated 3 times in 2023 is very promising, with scientists estimating that nuclear fusion energy will be able to solve widespread problems by 2050.
So how did the process work? It begins with weak laser pulses being split and carried to preamplifiers, or electronic amplifiers that boost a weak output into a stronger output by increasing the energy of it by a factor of 10 million. This amplifying effect is where beams go through large glass amplifiers where light is trapped. The glass amplifiers contain rare earth materials that are charged with energy from an external source, and when the laser comes through, the energy is passed on to the laser. The light travels back and forth through filters to ensure that it is the type of light we want. This entire process takes the energy of the light from 1/billionth of a joule to 2 million joules of ultraviolet energy. Then the light moves to the targeting chamber, where all the energy is focused on 2 forms of hydrogen, deuterium and tritium. This causes a super high energy explosion and high heat, which leads the 2 hydrogen atoms to fuse. The energy released can be equal or optimally more to what was put in. Since nuclear fusion doesn't create long-term dangerous waste, it is extremely appealing and can be used for a number of efficient technologies in the future. For example, nuclear fusion and propulsion provides a very high specific impulse, which basically means that it puts out more power and propulsion in a shorter unit of time and energy.
So if we produce large amounts of energy using fusion, why haven't we adopted it at a large scale yet? Well, the problem mainly lies within what we are fusing. As stated earlier, tritium is commonly used in fusion. However, it's a very scarce resource on our planet, and alongside the energy needed to initiate fusion with it, it's highly impractical to use it long term. Regardless, there exists a superfuel for fusion that happens to be abundant on the moon. Due to solar winds, the moon is rich in a species of helium called helium-3, which not only is great in quantity, but is also much more efficient than tritium. Still, obtaining massive quantities of helium-3 isn't as simple as going to the moon to get some, and major amounts of logistical improvements will have to be made before we can consider gathering it.
Nuclear fusion has the potential to revolutionize energy production by providing a nearly limitless, clean, and sustainable power source. Unlike current nuclear fission reactors, fusion produces minimal radioactive waste and carries no risk of catastrophic meltdowns. If successfully developed, fusion energy could drastically reduce reliance on fossil fuels, helping combat climate change while meeting the growing global demand for electricity. Future applications extend beyond power generation. Fusion could be used for space propulsion, enabling faster and more efficient space travel. It may also play a role in desalination and hydrogen production. While technical and economic challenges remain, ongoing advancement brings us closer to practical fusion energy, with experimental reactors paving the way for accessibility in the future.